Hello, everybody, and welcome to another Communication Systems Lab seminar. So today's seminar is with Professor Sasha Sherstov from the Computer Science Department. And he has won the UCLA-wide Distinguished Teaching Award. So he's a great teacher, and I think we're going to have a great presentation. And I want to explain why he's here with us. So there's this legislative body in the school called the Faculty Executive Committee, and every time a professor wants to start a new class, they have to present it to this committee of other engineering professors and to get it voted on as to whether or not we're going to let them start the class to teach a new class. And Professor Sherstov was presenting his class in the FEC, and the name of his class is Communication Complexity. And that's what we do. And I was thinking, my goodness, we're working on low complexity communications, and there's a whole class about it. You know, why are we not talking with this guy every day? So what I wanted to do is let him tell us about what he considers to be communication complexity and what his class is about. And probably we can all take the class and see, and maybe we'll find out that we actually have close enough interest that there might be a potential for us to collaborate on research. So I'm looking for, I have a feeling that that his ideas are not exactly the same as what we think of, but we're going to figure it out. So I think I'm just really excited to that. And I want to express my gratitude to Professor Sherstov for taking the time to come and speak with us on a Friday morning. So I'm going to go ahead and turn it over to you. Let me make sure that you have there. Anybody can share their screen now. And so so you can take it from here, Sasha. We're just so glad that you're with us.
All right. Thank you so much, everyone. It's a great pleasure to be here. I'm thankful to Rick for the invitation and for the generous introduction. Look, I'm ready to sing Communication Complexity from the rooftops any day. So this is, I'm super excited to be here. Okay, so we're computer scientists, engineers, computational mathematicians. And if you ask all of us, what is the most important computational resource, I'd say that most people would say time, computing time. And in a sense, that's true. Computing time is certainly the most studied computational resource, but depending on the context, on the exact application, it may not be the most important one or the most relevant one even. In practice, in computer science, we study a variety of other resources such as memory, the use of randomness, the use of quantum bits, the use of samples or learning data. There are a variety of other resources that may be more important to your application than computing time. And today we're going to talk about a specific resource that is particularly influential in theoretical computer science. And that resource is communication. Now, why study communication? There are two reasons. The first reason is the more obvious reason. Communication is a bottleneck, a common bottleneck that occurs in a variety of computational contexts, and minimizing communication is a beneficial thing to do. At a minimum, we should like to study this resource as a computational resource in its own right. The other reason is more subtle, and this is something that I hope will be borne out by this talk. This other reason is that just about any computational system can be split into two components, or maybe several components, such that there is information flow among these components. All right, and as soon as there's information flow, the operation of that system is subject to communication complexity results. And we can prove a variety of results, lower bounds and upper bounds for such systems if we understand communication as a resource. All right, so this is what this talk is about. It is, quite frankly, a shameless advertisement for a graduate class that I'll be teaching in the fall. I've taught it for about 9 or 10 years, and this time it will be the first official offering when it's an official part of the curriculum, and it has its own course number. So I'm beyond thrilled to teach it. Okay. Communication complexity was pioneered in 1979 by Andrew Yao, a Turing Award winner. And in the most basic model, Yao considered two communicating parties, call them Alice and Bob. And there's a function f with two arguments, x and y. They're both elements of some finite sets. X is an element of some finite set capital X, Y is an element of some finite set capital Y. And to keep things simple without loss of generality, let's say the function is Boolean. All of these restrictions are without loss of generality, and they keep the mathematics very clean. So we'll stick to them. Okay, so Alice and Bob, and they communicate back and forth to determine the value of the function. Alice receives the first argument, x, and Bob receives the second argument. So they actually need to communicate in order to compute f of x and y. Now, locally, they're allowed to use arbitrarily complex computations. They're computationally unbounded locally. The only resource that we're interested in is communication. I should say, throughout this talk, this is a very informal talk. Throughout this talk, if you have any questions, please feel free to interrupt, and I'll be happy to explain. It'll be particularly important later on for the later slides because some of the mathematics assume some background, which I'm not sure is the right assumption in all cases. So please feel free to interrupt.
Well,
Now,
I just want to say right away at the outset that one of our research teams is working on various ways to decode LDPC codes. And the key concept, or our key concept for reducing the complexity, is reducing the amount. There are a whole bunch of computational nodes, and they pass messages back and forth. And we seek to reduce the complexity by making those messages as compact as possible. And so this is an area right away where I feel like, we have not used the computer science framework explicitly, but I feel like these ideas, we're kind of swimming in that pond. So it'll be really fun to hear what you have to say.
Okay, so let me expand on Rick's point. This area is huge. It's vast. All right. This is a slide that shows some of the highlights that Yao's theory has led to. Now, it's been 43 years since he pioneered communication complexity. It has since found applications to the most unexpected computational phenomena. Chip layout, neural networks, graph theory, the study of Boolean circuits, the study of various quantum systems, computational learning, randomness, even data structures and streaming algorithms, various results for Boolean matrices and matrix analysis that are of interest to the linear algebra community, the study of combinatorial auctions and mechanism design. In fact, even algebraic geometry. So the sheer span of topics that communication complexity sheds light on is absolutely mind-boggling. All right. In this talk, to keep it focused, I would like to illustrate the power and complexity of communication complexity with a specific problem that runs like a leitmotif throughout the theory. Now, this is the most important, the most studied problem in the area, and one that is crucial to understanding communication as a phenomenon in a variety of settings. So this problem will be our example throughout this talk, and it will teach us so much about what communication is and how to study it. All right, the problem is the disjointness problem. Alice has some subset of the first n natural numbers. Bob has also a subset of the first n natural numbers, and their goal is to determine whether there's an integer that's common to their two sets. All right, this is a problem that we solve a lot in practice. Anytime you want to schedule a meeting, you implicitly have to solve this problem. All right, so Alice's availability is a subset of, say, the first n dates, and Bob's availability is another subset, and they'd like to figure out if there's a date that's common to their two sets. What we will see in this talk is that scheduling is a very difficult problem. Okay, it requires a linear number of bits of communication, right, which matches the trivial upper bound, even to achieve correctness probability 51%. So even to be marginally sure that there is a date that we can both agree on, even that is hugely expensive. And we allow all forms of communication here, right? Not just a message of the form, are you available on such a date? All right, so disjointness problem. The 43 years of communication can easily be called 43 years of set disjointness, because throughout the theory, major progress has been enabled by the study of this function. And we're going to look at the amazing story of set disjointness and the amazing story of communication complexity theory as they go hand in hand by looking at various models of communication. We'll start with the most basic, the simplest model, the foundation for the rest of the talk. And then we will look at increasingly more realistic, more practically relevant, and more technically sophisticated models. All right, deterministic communication. The key notion to understand in understanding communication is that of the characteristic matrix. All right, instead of looking at functions with two arguments, it turns out to be much more productive to speak of matrices. All right, so here we index the rows, the columns of the matrix with Alice's argument, and the rows are similarly indexed by Bob's argument. All right, so you have a matrix that is a finite matrix with rows indexed by Y, columns indexed by X, and the X, Yth entry is the value of the function at those two inputs. All right, why is this important? Well, it helps to understand the communication problem you are trying to solve. In this picture, blue cells correspond to false inputs and red cells correspond to true inputs. All right, so basically, to reformulate the problem, Alice is given a column index and Bob is given a row index, and they'd like to figure out the color of the corresponding cell. All right, let's think about what a protocol actually does. Now, the very first bit that gets transmitted in the protocol, let's say Alice transmits it. That bit is a function of her input, right? So as soon as that bit is received, implicitly, that partitions the matrix into two parts, right? Depending on the columns for which Alice would have sent a 0 and the columns for which she would have sent a 1. All right, now it's Bob's turn to communicate, let's say, and his message, 1 or 0, is also a function of his input. But this time, crucially, it is also a function of Alice's input. So when Bob sends his bit, the matrix gets partitioned like so. Now, in actuality, the partition may look a lot more complex because the columns and rows need not be contiguous, but it's awfully hard to draw something that's not contiguous in PowerPoint. So we're going to stick to this picture. All right, they keep going like this for a while. And at some point, the matrix gets split up into monochromatic submatrices. All right, so this is the first fundamental observation in the study of communication. Any cos-C deterministic protocol partitions the communication matrix into 2 to the C monochromatic submatrices. All right. Now, once we have this fact, we've gotten our foot in the door. We can try to understand now the complexity of basic functions. Let's look at disjointness. I claim, and the proof is actually quite straightforward, that the characteristic matrix of the disjointness function cannot be partitioned into fewer than 2 to the n monochromatic submatrices. Let's see why that's the case. Before we do, this theorem implies right away that you need n bits to solve this problem. All right. So if you want to be certain that there's a date that you can both agree on, you need to communicate n bits. Now, this matches the trivial upper bound, because what one of the parties can do is to just send a binary vector that indicates for each date whether she is available on that date. All right, so let's see why that's the case. This is your first proof in communication complexity. We're going to arrange the columns of the matrix such that they correspond to the sets S in lexicographic order. We need to fix some ordering. And the columns are likewise going to be indexed by the complement of S, where S is also arranged in lexicographic order. Now, when we do that, the diagonal entries are going to be all ones, because the diagonal entry is always S, comma, complement S, and S and complement S are disjoint. Now, I claim that for any 2 diagonal elements, you cannot put them into the same, you cannot have a monochromatic submatrix that contains them both. Why is that? Well, consider 2 diagonal elements, S comma complement of S.
Can I ask a question? Because I'm missing something. So maybe other people might be missing it too. So the 1s and 0s are the results of, in the matrix, are the results of the function evaluated at X and Y, correct?
Right.
Okay, so my function can be any function, I thought. So I guess what I really think is I just don't know what S is. Why is it that F of S complement of S has to be 1? I didn't get it.
Okay, so we're studying a specific F here. We're studying the function F, which is the disjointness function.
Oh, I'm sorry. Of course.
Yeah.
Well, I just asked a really stupid question. Got it. Okay. Yeah. So
this is a fantastic question. There'll be lots of instances throughout this talk where if someone doesn't ask a question, I'll go too fast or I won't elaborate. So I'm hugely thankful for every question you guys ask. This is so important. Okay. It gives me peace of mind knowing that you can chime in at any point and ask a question. So please do. All right. So
you have an ordering for the sets, whatever lexicographic ordering, but whatever set whatever lexicographic ordering you impose, then on the y-axis, it's not that set, it's the complement of that set. So it's always disjoint. In fact, it is the largest set that would be disjoint. It's
right.
One of the sets there would be other sets that would be disjoint, but this one certainly is. That's
true. That's true. That's exactly right. Okay. So I claim, let me back up a second. So the diagonal elements are 1. Now I claim that you cannot have a monochromatic matrix that takes in 2 diagonal elements. Why is that? Well, suppose we could find 2 such diagonal elements, S comma the complement of S and T comma complement of T. S and T are different sets. This means that either S has to contain some elements that T doesn't, in which case the complement of T will have non-empty intersection with S, right? In that case, you'll have a 0 in this yellow submatrix. That's the first subcase. The second subcase is when T has some elements to offer that S does not contain. In that case, the complement of S will have non-zero intersection, non-empty intersection with T. So the upper right-hand corner will be 0. All right, so the matrix cannot be monochromatic. One of those two corners is going to be a 0. The bottom line is that no matter which two diagonal elements you choose, you cannot squeeze them into a monochromatic matrix. They require a dedicated, separate matrix to cover them. All right, so that's the conclusion.
So I guess the thing that I was, and I guess it just hit me. So the whole, our focus on the disjointness problem, it does. So when you say that, oh, this is always hard, it's always order n, it's the disjointness problem. There are other problems that are going to be beautiful. And like if I have my specific problem, I might have a matrix that is that has just a couple of monochromatic regions, and I can quickly solve it. So there are easy, or at least it seems to me like there could potentially be easy communication problems where I get a big win by doing this analysis. It's just that this disjointness problem isn't like that.
Yeah, absolutely. Right. So historically, communication, the thrust, the emphasis of communication complexity has been on impossibility results and lower bounds. But there are a variety of upper bounds as well. So you're right. Other problems in communication have very efficient protocols. The ones that turn out to have the most applications in theoretical computer science are typically the hard communication problems, because that translates into impossibility results in other areas. Okay, so we have our first communication lower bound, and now you guys can officially consider yourselves to be students of communication complexity. All right, to illustrate just how multifaceted the phenomenon of communication is, I'll show you another proof, which is very short and which has nothing to do with combinatorics, which is linear algebraic instead. All right, so when you look at any communication matrix, it has zeros and ones, and you look at a communication protocol for it, which partitions it into monochromatic submatrices. That gives you a decomposition of the matrix into a sum of rank 1 matrices. Right? If you can split it up into, let's say, m parts that are monochromatic, that gives you a representation of the matrix as a sum of m matrices of rank 1. That means that you need at least the rank of m submatrices. You cannot do with fewer submatrices. So this suggests a linear algebraic line of attack. If you look at the characteristic matrix of set disjointness, you realize that it has very good, very strong recursive structure. All right, so here, instead of ordering the sets in a specific way, I'm splitting the columns into two groups. The first group contains the nth element. I'm sorry, this first group does not contain the nth element, and the second group contains the nth element. And similarly for the rows, the first group of the rows is going to correspond to sets that do not contain the nth element, and the second group is going to correspond to rows that contain the nth element. All right. This means that the bottom right-hand corner is going to be a matrix that's identically 0. And the other 3 quadrants are going to be like problems. They're going to be the set disjointness problem on n-1 bits. All right, as soon as you have that, you have factored your matrix as the nth Kronecker power of this simple 2 by 2, right? By induction, because you can repeat this. And this 2 by 2 has full rank. You raise it to the nth power and nth Kronecker power. So the matrix has rank 2 to the n. This is a completely different proof of the same combinatorial fact. Okay, so now we know that the deterministic communication complexity of this matrix is very high. It turns out that rank not only is not only helpful in the study of this problem, it is believed that in fact it is a tight characterization of the communication complexity of every problem up to polynomial factors. So there's a famous conjecture in the area that states that the deterministic communication complexity is bounded by a polynomial in the logarithm of the rank of the matrix. What we showed is a lower bound that essentially matches this conjecture, but we believe that the upper bound also holds. So this is a major open problem in the area, and there is overwhelming evidence to suggest that it is true, but it is unproven yet. Okay, so the best known gap uses the set disjointness function in the construction. Okay, let's keep going. Let's now look at a model that is slightly more complicated, non-deterministic communication. Here, Alice and Bob each get their argument to the function, but in addition to their arguments, they can now send coin flips. Coin flips are non-deterministic. You can think of them as well, literally flipping a coin and sending the outcome via the wire. Now, the requirement is
Can I
that...
ask you a question? So
Yeah.
that's very similar to the binary symmetric channel.
Mm-hmm.
Okay.
Yeah, I mean, it probably is. I'd have to...
Yeah, so binary symmetric channel says y is x plus z, where x and z are independent and z is distributed as Bernoulli of P.
Okay, right. So here there isn't a distribution on the coin flips. There are arbitrary coin flips. The success criterion is that the protocol has to be correct no matter what coins they flip when f evaluates to 0.
Can I want to ask, are we so you're not really sending, sometimes there are other communication channels that we've studied where you actually hand the other side a coin and the other side flips it. But I think what you're describing is that Alice flips her coin and transmits the result.
Right. She can
So
flip the coin locally.
That's a distinction. But the question I wanted to ask is Alice allowed to use a bent coin, or are these 50-50 coins?
Oh, she can use a biased coin.
Yeah.
Right. So she can do anything.
Any
But you know,
coins. Okay.
yeah, but she's charged for the communication. So if she wants to transmit, say, a very biased coin, then she may need to think about how she wants to encode it. So the success criterion, once again, is that you cannot have false positives. You cannot have false positives.
She's going to send the bit, so she's going to send a bit regardless. So isn't it still a bit whether she uses a bent coin that's very bent or doesn't flip a coin at all? She's just going to send one bit.
No, I guess you're right. I mean, in fact, the idea that the bit may have some distribution here isn't really going to save us any communication, because the criterion is that if F evaluates to 0, you're required to be correct, no matter what coins you flip.
So what I think, just to kind of set up the tension here, I mean, so I'm wondering, I mean, I know we have lots of cases where randomness helps a lot, but there's the part of me that is wondering, well, why would I ever do that? Why would I how is randomness going to help us to get a better result? So I'm excited to have you tell us.
Oh, wow. Randomness is hugely helpful. Look, there are a variety of problems. You know, there's a textbook example, and that's one that I use to advertise this course to students who don't have any exposure to theoretical computer science. Let's say you have, so Rick knows this example, but I'm going to tell you guys. Let's say you have two parties, Alice and Bob, and they're geographically separated, and each of them has a copy of a gigantic database, and they want to figure out whether the databases are in sync, whether they're the same database. Now, if their databases are, let's say, copies of Wikipedia, that's about 6 terabytes at this point. Even if they use the fastest satellite link, the most expensive communication channel, it'll take them about a week to transmit it fully. So even with the fastest technology. Now, if you use randomness, it suffices for you to exchange 8 bits. 8 bits, and you will figure out whether the databases are the same or whether they're distinct. You will figure it out with probability of correctness 99%. Just by spending 8 bits. Okay, you won't have 100% accuracy. It's a randomized solution. But the point is, nothing is 100% accurate in this world. Planes aren't 100% accurate. Buildings aren't 100% accurate. If you repeat this experiment, let's say twice, then all of a sudden, your probability of error isn't 1%, it's 1/10,000th. Right? So if you repeat it 3 times, you've invested 24 bits, and your probability of correctness is 1/10⁶, 1/1,000,000th. All right, this is just to illustrate the power of randomness. And you know, even if there's a disagreement in 1 bit, you will catch it with overwhelming probability. This is the simplest example where randomness helps. There are a variety of sophisticated ones where, you know, it's not that it should be relevant, but you know, it turns out to be hugely helpful. Exponential savings, right? And randomness is going to be a highlight, sort of the culmination of this talk. Right after non-determinism, we will move to randomness, and that'll be the culmination. In non-determinism, though, the criterion is that you cannot have false positives. When you say that the function is 1, you know, it better be 1. You can have false negatives. That is allowed, right? If the function is 1, you're allowed to sometimes output true, sometimes output false, as long as there's one computational path that outputs true. But if the function is 0, then you must output false in all cases. All right, so this is sort of a fundamental notion in theoretical computer science, one that we obsess over. The P versus NP question and its generalizations are all about the power of non-determinism. We in computer science think that non-determinism is the right formalization of human creativity. And you know, there are various cultural reasons why non-determinism is so important to us. All right, let's see what that means for communication. Maybe if Alice and Bob are not deterministic, maybe then they can schedule that meeting more efficiently. Well, just like a deterministic model partitions the matrix into 2 to the C monochromatic submatrices, a non-deterministic model covers the ones of the matrix by 2 to the C monochromatic submatrices. Let me say what that means. So on the right, you have a partition with 3 red rectangles. On the left, on the right, you have a cover of the red rectangles with of the red cells with 2 red rectangles. So the point here is that if you just look at the red cells and you wanted to cover them without overlap with submatrices, you need at least 3 submatrices. But if you allow overlaps, then you can do it with 2 submatrices. So this is intuitively why non-determinism is more efficient than deterministic communication. Note, however, that these rectangles cannot contain a blue entry. In randomness, they will be able to contain blue entries, but here they have to be pure that way. All right. So it turns out that disjointness cannot even be covered, not just partitioned, but even covered by fewer than 2 to the n monochromatic submatrices. And the proof you already saw, right? This was Yao's original proof. And this means that the non-deterministic complexity remains n. Let me give you a very different proof that showcases the sort of the richness of this problem. The lower bound is slightly weaker, but the technique is much more widely applicable. All right. So we're going to put the uniform probability distribution on the ones of the matrix. So the red entries of the matrix, we're going to put the uniform probability distribution on them. And then we're going to say, well, let's look at any submatrix of the set disjointness matrix that is all red. All right, so it is monochromatic. It consists of red entries only. That means we have a family of sets, script A, corresponding to Bob's, let's say, inputs, and a family of sets, script B, corresponding to Alice's inputs, such that for any set from Alice and any set from Bob, that corresponding pair are disjoint. All right, I claim that you can't have a submatrix that's large. In other words, the product of the cardinality of script A and the cardinality of script B will be pretty small. Let's see why that's the case. Well, so what is the measure really of this submatrix? It's the cardinality of this cross product divided by the weight of a single entry. The weight of a single entry is 1 over 3 to the n. It's something you can verify as an exercise. The number of pairs S comma T, where S and T are disjoint, is precisely 3 to the n. So the denominator is 3 to the n. The numerator we can bound very easily. Once you have a family of sets, script A, you can form, so you can consider the union of all the elements that they contain, and you can then enlarge the family to contain all subsets of that subuniverse. All right, and similarly, you can do it with script B. The resulting enlarged submatrix will remain monochromatic. On the other hand, these two subuniverses have to be disjoint, and together they account for for n elements for the entire universe. So this gives you an upper bound of 2 to the n divided by 3 to the n on the measure of any monochromatic submatrix. All right, so for non-determinism, this proof is overkill. the original proof by Yao was much simpler, but this is setting the stage for the culmination of the talk, where we talk about randomness. And there, these techniques will be quite important. All right. Now let's let me say briefly about the significance of this result. You can classify communication problems into groups according to the resources that they require. So here we have the class NP, which is the class of communication problems that have efficient non-deterministic protocols. And analogously, the class co-NP, which is problems whose complements have efficient non-deterministic protocols. It turns out that the deterministic communication complexity of any function is at most 4 times the product of the non-deterministic and co-non-deterministic complexities. So if both a function and its complement have efficient non-deterministic protocols, then the function has an efficient deterministic protocol. And conversely, this is a very surprising phenomenon. We are not aware of any such phenomenon anywhere else in the realm of theoretical computer science, in the realm of computation. But in communication, it holds. This means that the class P corresponds to the intersection of these two classes. And you can show that this is the best possible result by studying a variation on the set disjointness function. So if you analyze specifically the complexity of set disjointness, for deterministic, it's n bits, n plus 1 to be precise. For non-deterministic, it's n. And for the complement of set disjointness, all you need is log n bits. The complement of set disjointness is set intersection, where Alice and Bob want to figure out whether there's an element that's common to both of their sets. And for this, they can just guess non-deterministically the name of an element of the universe, and then they can both check with 1 bit of communication whether that element is contained in both of their sets. So describing an element of the universe is log n bits, and then checking whether it's contained in both of their sets is another, say, 1 or 2 bits. And this gives us the following satisfying conclusion, that disjointness separates co-NP from P. And the complement of set disjointness separates the class NP from P. So, it arises as an extremal example in so many settings and helps us understand so many computational phenomena. All right, so as promised, now we're going to dive into the deep end of the pool and talk about randomized communication. So here you'll see things get quite subtle and mathematically deep and beautiful. All right, in randomized communication, this is what Rick was alluding to earlier in the talk. Parties can send coin flips, and the error probability is required to be at most 1/3 on every input. You can also consider a variation on this model where the parties do not send coin flips. Instead, they both observe a shared source of randomness, and that shared source of randomness governs their computation. The difference between these two models are basically non-existent. All right, so it's surprising, but it turns out that it doesn't make a difference. And shared sources of randomness are abundant in nature. For example, you can observe electromagnetic phenomena on the surface of the sun, various phenomena on the surface of the earth that we believe are truly random, and extract randomness that way. So, okay, maybe randomness will allow us to schedule that meeting more efficiently. It turns out, and this is what you'll see in the next 2 or 3 slides, is that a randomized protocol is not any more efficient for this function than deterministic or non-deterministic. So this is really a problem that holds fort. Well, okay. So what is a randomized protocol? A randomized protocol of cost C is conveniently thought of as a probability distribution on deterministic protocols of cost C. Right, depending on what they observe on the surface of the sun, they execute the corresponding deterministic protocol. Right, so you can think of it, in terms of this schematic. They flip a coin, let's say a 3-sided die, and depending on the outcome, they execute the corresponding deterministic protocol. Now, in reality, it won't just be a 3-sided die; it'll have, a huge number of sides. Any finite number is fine. We don't charge for it. So even if they want to sample from an infinite source of randomness, that is perfectly fine. Okay, so let's now talk about how you actually prove that a randomized protocol must be inefficient, cannot have an efficient solution. For this, you need a famous idea in, economics originally, but it's adopted throughout computer science. It's the minimax principle, which states that to prove that a randomized problem is hard, it is necessary and sufficient to find a probability distribution on the domain of the problem for which the problem is hard for deterministic protocols. All right, so this passage from dealing with randomized problems to dealing with deterministic problems with respect to a given distribution, that is the magic of the minimax principle. And it turns out that it's an exact equality. It follows from the zero sum theorem from the theorem on the zero sum games. Now, concretely, what we need is the following result. Its proof is fairly short, something that we won't go over in this talk, but it's intuitive, and you can take it on faith for now. So suppose that we can put a probability distribution on the ones of the function, so on the pink entries of the matrix. You can put a probability distribution on all entries of the matrix such that the pink entries have non-negligible weight. Here, let's say they account for 1/100th of the total weight. And let's also assume that the distribution is so constructed that every submatrix M is corrupted by zeros. In other words, the weight of the zeros inside any submatrix is at least 1/100th of the weight of the ones in that same submatrix, minus some tiny error term. That means that all matrices that are larger than delta are going to be at least 1% corrupted by zeros. And if you wanted a protocol that achieves error probability better than 1%, you would have to use only those submatrices that have measured delta. And therefore, you would need at least 1/delta of them, and the communication cost would be logarithm of 1/delta. So this is sort of an intuitively satisfying criterion that we can take on faith for now. So the lower bound that I'll sketch in the next couple of slides, is it okay if I go for another 5 minutes? Do we have that? Okay, all right. So this is the lower bound Oh, sorry, Rick. I think you're on mute.
I was gonna say, it's fine for you to go a little bit late. We're recording it, so we'll have it for people to watch later. But some of our audience might need to go to a 10 o'clock class, and so it's just fine
Okay.
if they have to leave.
Okay. All right. Okay. Thanks. Thank you. All right. So this is the lower bound that will show, and you'll see that the mathematics gets subtle here. The lower bound is not tight. It can actually be improved to a linear lower bound, and you can even figure out the multiplicative constant in front of the n. But for the purposes of this talk, this is quite illustrative. All right. So what are we going to do? We are going to consider. We're going to make the problem easier on Alice and Bob. We're going to guarantee that their sets have cardinality root n. All right. In general, they're required to solve the problem for sets of all cardinalities. Here we're going to say, Alice, your set is guaranteed to have cardinality root n. You just don't know which set it's going to be. And Bob, analogously, is guaranteed that his set will have cardinality root n. He just doesn't know which set it's going to be. And they have to figure out whether their pair of sets are disjoint. So we have to prove that every monochromatic submatrix is going to be corrupted by intersecting pairs. Now let's think what that means. Think about what that means. So let's say we have found a monochromatic submatrix that is large and is, so the rows are indexed by some family of sets script A, and the columns are indexed by some family of sets script B. All right, so we're going to prove that the measure of this submatrix is going to be exponentially small. If the submatrix has at most an epsilon fraction of offending elements, so it's a very accurate submatrix, then that submatrix will have to be very, very small. Think of this as a floor that's tiled with tiny tiles, and they're sort of colored black and white, right? Now, if you take a large rectangular region that contains many tiles, you're not going to get, they'll be balanced. You'll have about 50% whites and 50% blacks. If you wanted to pick a submatrix that, has just about every tile, in which just about all tiles are white or all tiles are black, for this, you would need to stick to very, very, very small submatrices. All right, so this is something, or, you can think of TV static, and, you can think of picking a matrix on your screen that contains as many pixels as possible while keeping it monochromatic, approximately monochromatic. So we're going to prove that the measure of any such submatrix is going to be exponentially small. Specifically, let's assume that the measure of the family script A is going to be non-trivial, is going to be 2 to the minus epsilon root n of the total weight. We will then prove that the measure of the family B has to be trivial, has to be exponentially small for some constant epsilon. So the product of these two things will still have to be small. All right. So first of all, I'm going to remove any row in which the fraction of offending entries is greater than 2 epsilon. So in the entire submatrix, the fraction of offending entries is at most epsilon. I'm going to remove any row in which that fraction is double the average. Okay, that means that I have kept at least a half of the rows. All right, then I'm going to so I still have a large collection script A. That will allow me to identify inside this family of sets, script A, a subfamily that is well separated. All right, so originally I had this gigantic family, script A. It had exponentially many sets. I'm going to remove just about every set from the family except for a very, very, very small collection of representative sets. So I will only keep root n divided by 3 sets. I used to have exponentially many. Now I have only a very small number. But these sets will be spread out in the sense that the ith set is going to have at least half of its elements that are not covered by the sets A1, A2, A3, all the sets up to AI. This is something that you can ensure with a combinatorial argument. It's an application of the so-called probabilistic method. And pictorially, what does that mean? Well, if you draw these sets, they may have overlaps, but it'll be a fairly, the overlaps will not be too large. Okay, so I've thrown away some rows. I've thrown away a lot of rows, in fact. Now we're going to deal with the columns. I'm going to throw away all the columns in which the fraction of offending entries exceeds 4n. Okay, I've thrown away only at most half of the columns that way. And now I'm just going to count the number of columns that I can possibly have. Well, every column corresponds to a vector in which the fraction of offending entries is at most 4 epsilon. How can I pick such a vector? Well, I pick the locations of the offending entries, right? And that corresponds to a choice of the sets that I'm allowed to intersect. Once I commit to using just those sets and not intersecting the other sets, then I have forbidden myself to use a huge chunk of the universe. Because, so once again, the offending entries here are the blue entries. I'm only allowed to intersect. So I pick a subset of the coordinates for a 4 epsilon fraction of the coordinates. That corresponds to coloring some of these A's blue. Now the other sets are then colored pink, and the union of those other sets we cannot intersect. This means that we have basically forbidden ourselves from using a huge chunk of the universe, because together those pink sets account for about an n over 6 elements. That's because the sets are spread out. So whichever say m sets you pick, together they're going to have m times the square root of n divided by 2 elements because of this well separation property. All right, so this gives us the following bound on the size of B. We first pick which of these A's we're allowed to intersect. All right, that immediately restricts the size of the universe that we're allowed to choose the set B from. And when you consider this product, you realize that it's actually an exponentially small fraction of all possible sets of n choose root n. All right. So this is a sketch of this theorem. We spend a a 2-hour lecture proving it in communication complexity. So this is something that is quite difficult to grasp so quickly. And once you have this corruption lemma, you get the result that the randomized communication is root n, because the probability distribution places constant weight on set pairs that are disjoint, and you have the corruption property for all submatrices except submatrices that are exponentially small. All right, so now we can triumphantly add a new circle to the to the diagram, BPP. That is a new abbreviation that has great significance in computer science. It's the class of all problems solvable by an efficient randomized algorithm. And what we have shown, so these are results that you can show fairly easily. What we have shown is that, in fact, all regions of this Venn diagram are non-trivial. So disjointness gives you a separation of coin P from P, and it's outside of BPP. The complement of set disjointness will separate NP from BPP and coin P. Okay, so there's a lot of subsequent work. I mean, I barely scratched the surface of this area. I could easily go on for another 2 hours. There's a ton of slides that maybe I'll just flip through.
I think you've done a great job of giving us a taste of the kinds of problems that you'll be addressing in your class. Can you remind everybody what the number is for your class? Is it going to be offered in fall?
Yeah, it'll be offered in fall. I think the number is 285 CC for communication complexity. And I can put it in the chat just so we have it there.
And it's a graduate class in computer science. So what are the undergraduate classes that you assume that people come in knowing about?
Okay, yeah, that's a great question. What I actually do is, so let me start by saying that engineering students, every engineering student I have worked with so far has amazed me with their background and their dedication and their just intellectual strength. In computer science, we sometimes have students who don't have the background, and they sign up and they realize that it's a lot mathier than what they bargained for. So what I actually do is I like to schedule a short one-on-one with every student who wants to take this class, just to discuss their background. If people are still not sure what I can do, something that I've done in the past regularly, and people really appreciate it. I give them a short background assessment, maybe an hour or so, just to complete on their own. And they'll see, whether they have the required background. Now, anyone with a math major will comfortably follow this class. I try to keep it as self-contained as possible. In fact, I have even had undergraduate students take it and do extremely well, provided they're motivated and they have the time to put in work into this class. So that's
the prerequisite. Do people need to know? Sounds like probability would be a great thing to know coming in.
Okay, so
what about modern algebra, or don't need modern algebra?
All right, so abstract algebra would be great. I mean, the first half of the course deals with abstract algebra quite a bit. Things like fields, groups, that would be very useful knowledge, and then just general preparation like linear algebra, probability theory, combinatorics, analysis. So for the real analysis, we for the second half of the course, we'll use less combinatorics, less abstract algebra, and more real analysis. So we'll be using matrix analysis, Fourier analysis. So taking a course in real analysis would be very helpful.
Got it.
But for the most part, having a strong motivation is by far the most important factor. And once again, in computer science, we do have situations when students aren't as strong mathematically. Now, in engineering, at least in my experience, I think engineering students tend to have vastly stronger mathematical background than their computer science counterparts. That's been my experience in my 10 years at UCLA. So I don't envision, I've had so many engineering students in my classes, computational complexity, communication complexity in the past, and not one of them has struggled. I have had computer science students, master students, for example, who have struggled because they have deficiencies in their math background. So, but anyway, so if you want to chat about it, just get in touch as fall approaches. Say the week before the fall quarter, we can schedule a one-on-one. I can send you like I said, I can put together a background assessment, and if you like, you can even say attend the class without a grade. I welcome auditors as well. So just
Thank you. Oh, that's great. We appreciate the welcoming nature of the class, and it's just been great to have you come and tell us about it.
Yeah, thank you so much. I really enjoyed it. So just to give you a super, I know I'm already trespassed. I know I've overstayed already my welcome, but real quick, just to give you a very brief highlight of what we haven't covered. Multi-party communication is something that we haven't even touched on. And that is a current frontier in the area. Now that requires a completely different approach, and there are open problems that would warrant, say, a Nevin Linna Prize if solved. Anyway, I'll leave it at this, and thank you so much. I hope to see some of you in the fall. So the class, I think, has a cap of 25. Historically, we've never hit that many students because it's a challenging class. So don't worry about, getting in. If you want to take this class, you will get in, no question about it. It's just a matter of it being a good fit for you and it being interesting for you. Okay, guys, I'll see you in fall.
Yeah, thanks a lot. I think our students would definitely have the probability and linear algebra. Every engineer has that. Oh, yes, let's give the virtual applause. I like that idea.
Okay.
But the real analysis, our graduate students typically end up taking real analysis. Our undergraduates probably wouldn't have had the real analysis unless they went out of their way. But like Amael was a math major as an undergraduate as well. So he would have all of that background. So it's interesting. And I do think that it's fun for me to see how different the setup is than sort of what we I work in communications and electrical engineering, but I think that it really I think that the way that it's different is so fun. It would really add something to the work that we do to bring these techniques and this understanding. So sometime over coffee, I'll have to talk to you about the things that we worked on that feel so close to what you're talking about, even though we didn't really even think about bringing in this computer science perspective to that work. So I feel like there's definitely work for us to do to sort of bring the two areas closer together. Anyway, so much fun. Thank you so much, Sasha.
Yeah, thanks so much, Rick. I remember that faculty executive committee meeting. I was presenting communication complexity, and Rick was like, wait a minute, communication. That's exactly what we do. That's what we do all day. Okay. Okay. Bye-bye, everyone.
Okay, thank you. Bye-bye.
Thank you.
Thanks for the talk.
Mhm.